I'm going to present a program, or at least a good part of this program today, on system safety grounding. Just a little bit about me for those of you who might not know me or ever heard of me. I'm not on the post office wall anywhere, so I'm legal, and I'm not wanted by anybody, I don't think. So anyway, I retired from Georgia Power after 40 years and 6 months of line work. I was a lineman for about 19 years, and then a foreman, crew leader. And then I went into field safety, and I wound up retiring as a safety consultant for distribution and transmission. Had a great career, worked with some of the best people in the industry, worked with one of the best companies in the industry as far as I'm concerned, and never regretted a moment of it whatsoever. When I retired, I immediately opened up my consulting company. I left a little early, and I opened up my consulting company, and I hired 3 or 4 of the people that worked with me at Georgia Power that retired about the same time I did, or a little later. And now then we have Raines Utility Safety Solutions. Secondary to that, I teach the 1910-269, arc flash, low voltage, electrical, all the electrical programs, or some of them, at Georgia Tech, the OSHA Outreach Center in Region 4 in Atlanta. So that keeps me busy a little bit. And then also contributing writer for incident prevention. If you take Incident Prevention magazine, if you don't, you should. It's free. There's not many things in this world that's free, but all you have to do is register and get the Incident Prevention magazine. And there's a series of articles in there every month that basically is directly related to what we do in the electric utility industry, okay? So I think you'll be very pleased with that. But I get Carla House has kindly asked me to write articles, and I think the last article we put in there was about installing fiber optics communications cable inside the supply space, the 269 supply space, based on the National Electrical Safety Code requirements. You'll find that pretty interesting. I know a lot of my cooperatives, electric cooperatives, are actually doing that. So I'm still asked occasionally to do witnessing for different cases in electrical incidents where people has been hurt, damaged, or even killed. And that's one of the things that probably keeps me going. I really enjoy that, but it's really very trying. And that's one of the reasons I like to take the time to do what we're doing today, is to try to educate people. When you can avoid accidents, why do you don't get paid to get hurt? You know, I've always tell people that everywhere I go. We get paid to work, and we get paid by the hour for the most part, and it's worth the time to take the time to do it correctly and safely the first time. So that, and then the CUSP program, I've been involved in it since the inception back in 6, 7, 8, I'm not sure how long it's been. It's been 10, 12 years since we started developing it and then presenting it. And then of course COVID, and now it can be done online. David McPeak's doing a great job there, and he's providing the online practices as well as the test. And now we don't go and actually do a presentation on the topics of the class and then proctor the test on site. You can do it online. It's easier and simpler to do, and it's very beneficial. One of the things that I really like, I noticed on LinkedIn, I've been off of LinkedIn for quite a while. I got back on it, and so many people now has that alphabet city behind their name, the CUSP, which I think is the greatest thing that's happened to the industry in a long time. And I think this program here will really help. So with that, that's enough about me. Let's get on with the program, and we're going to talk about system, equipment, and grounding. Main thing is the system grounding. And I start off very basic. My program, you know how to ground, and you probably already have a grounding program. You probably have a grounding policy. And what I have discovered, and this is one of my more popular topics that I'm requested to present across the country, and it's most linemen, you know, that I talk to, they don't understand the why behind the what. The what is grounding. Why does it work the way it does, and why do I have to do it a certain way? And then there's also other, I guess, challenges, like systems. We don't have just one system. We got one regulation that basically covers all systems, whether you're a delta or whether you're a multi-grounded Y system or a 5-conductor Y ground system or a single conductor, earth and ground return system. But we only have one regulation that kind of requires us to do grounding. Remember this, OSHA regulations are the minimums when it comes to work practices. They are the what and the why. They are not the how. Where do we find the how to ground and ground safely and most effectively to keep us safe while we're doing the work? And we have to go into the consensus standards, the ASTMs, the IEEEs, all of the other consensus standards that OSHA refers to in the OSHA regulations. And that's what I want to focus on today, is the why behind the what. You know what to do, you know when to ground. Do you know how and why those grounds work the way they do, and what's the safest manner in which you can actually install? There's a lot of reasons out there. People say, well, I don't have time, and gosh, it will only take a minute. I'm not a sissy. You wouldn't be surprised what some of the comments that I've gotten on feedback and critiques on some of the classes. And I've had some very experienced 20, 25, 30-year linemen. I've been in the business for 54 years, so I've heard most of the reasons. Okay, believe me. So it's amazing when somebody tells me that, I know my limitations, or I know what I need to do, or I don't need to cover this, or I don't need to ground that. I'm only going to take a minute. I'm going to work it like it's hot. All those things. It's easy to get from here to there, okay, in the cemetery. I like to quote people that's smarter than me. Ben Franklin was one of them. Tell me something, I may forget it. Teach me something, and I might remember it. But if you involve me, this is lightning rods, and you know what they are. They're on top of houses and silos and barns all over the country. How do they work? Here we go into the theory of grounding. So bear with me. Stay with me right here. How does a lightning rod work? And most people say, well, it gives a lightning rod path to ground. No, it does not. And Ohm's law in physics tells us that's not the truth. Well, in the first place, the wire there that's coming from the lightning rod to the ground is it's like a piece of 1/0 19-strand copper. And on a good day, that might be worth about 300 amps of fault current. So how much voltage and fault current is in a lightning strike? Much more than that can take, believe me. Okay. We had lightning strike a 500 station one time with my company, and I got to the station and the 500 locked out, which is, that ain't supposed to happen either. And the frequency meter registered 200 cycles, it pegged, and then the voltmeter registered 2 million volts, and it pegged. And that was one lightning strike. So now the lightning rod is the first attempt to equalize potentials. That's what we have to do in a grounded work scenario. In a work scenario, is to keep everything at one potential. If you only have one potential, you can't have current flow. And if you don't have current flow, then you can't get hurt. Okay, so it's as simple as that. When you look back at what the slide is saying right here, that lightning rod does exactly what I was just talking about then. It basically is there to give the potential path to a lightning rod which can trickle upward, okay, and equalize the differences of electrons from the ground to the cloud before the lightning strike occurs. That's equipotential, I believe. In paragraph N of 1910-269, N3, matter of fact, grounds shall be placed in such locations and arranged in such a manner that there will not be any hazardous differences of potential to employees. And that's kind of paraphrased, but it's pretty close to verbatim as to what the regulation is. But when you read that regulation, and we'll see it again in a minute, it does not tell you what size, how many, where to put them. It doesn't tell you any of that. It just says ground. And that's what I was talking about earlier. The how-to is found somewhere else. So let's look at system grounds. I want to make a comparison to electrical grounds. First, I want to establish a fact. Grounds trip electrical systems. Now, a good friend of mine, and many of you probably know him, Jim Vaughn, and I, we'll be in Orlando at the IP conference in April, and we'll have a breakout session on system grounding, and we'll have 125 people in there probably that'll be talking to us And what we do is sit there and field questions about grounding and tips and everything else about it. One of the statements Jim makes, and I concur with him, grounds never saved anybody. Grounds operate systems. Bonding is what saves your life. Now then, I know that's food for thought for you, and that may cause some conversation. So just remember that as we go through. Electricity takes the path of, and if I was standing in front of you right now, somebody would say the path of least resistance. No. Sorry to ruin your day, but electricity takes any and all conductive paths, and the amount of current flow on the path is dependent on the impedance and resistance on the path. Now we're going to introduce a little bit of the law of parallel resistances. Okay, so let's just look at it. Ohm's law and then Kirchhoff's law. Dr. Kirchhoff was a Russian physicist, and he came up with a theory of current division. If electricity, a ground on a line is not a dam on a river. That's kind of the way you need to look at it. It doesn't stop the flow of electricity, okay? The ground on the line gives the electricity for a current path to get the fault current back to the source as fast as it can on an assured grounding path, and that's either through a neutral or through, if it's a driven ground, or we'll talk more about that in a little bit, whether you use a temporary screw ground or a temporary pounded in ground, and the pitfalls of that ground. Of course, the neutral on a Y system, multi-grounded Y system, is by far the best ground, without a doubt, okay? It also introduces other challenges, but we'll get to that later on. So Kirchhoff says the current's going to divide based on resistance and impedance in the path. Ohm's law says electricity takes any and all conductive paths. Temporary grounds are nothing but an electrical circuit. That's really all it is. It basically is it's for a protective scheme. It gives a current, a conductive path for fault current to flow in. Let's look at low voltage for just a second. Now we have a construction standard, we have a maintenance standard for utility systems. 1926-950 subpart B and 1910-269 for maintenance. All right, 1926 subpart B came along in 1974. The first version of 1910-269 finally hit the Code of Federal Regulations in 92 to 94. It took them a couple of years to work out the wrinkles in the sheet. In 14, they updated it. So basically, they told us how to build it in 74. 20 years later, they told us how to operate it. And then 20 years later, they upgraded the operation and maintenance of it based on, the conditions changing and the science and things that we've learned in the system. But why is there two different electrical standards? You got 1910-300 for low voltage and 1910-269 for high voltage. 600 volts is the breaking point. Why? There we go. Raines is asking why again. He always does that. Well, the thing about low voltage system, in a 120 volt receptacle in that wall that you're sitting in that room looking at, or wherever you're at, long spade, short spade, and a round hole. So you got a neutral, which is the ground edge circuit. You got a short spade, which is the hot leg, and the round one is what? That's the grounding circuit. Okay, that basically is that assured grounding path to make sure fault current. The only time any voltage or current flow is on that grounding conductor is when? It's usually whenever whatever you have plugged into that receptacle faults, if there's a fault on that piece of equipment. So let's change gears a little bit. There's what's in the wall. That's 1910-304, that's grounding, okay? Let's look and see about this statement. It ain't dead till it's. They told me a lot of things when I first went to work at Georgia Power back in 1967. I was 3 years old, so I had to pay attention. That's a joke, and I hope you laugh. But anyway, we'll go on. It ain't dead when it's grounded, folks. I'm just telling you now. I'm gonna pop another bubble for you, because even when you put grounds on it, if there's induction or capacitive coupling or feedback or anything else out there, you still can have a different potential and it can be dangerous to us. Current flowing through grounding parts will kill you just as fast as energized conductors. Induced voltages, circulating current on grounds, accidental re-energization. We're going to give you some examples on all that in a minute. I hope you can see that okay. Okay, I think there's like 5.6 amps, 5.7 amps on that amp meter right there, and that's on the ground. I thought it was dead if it was grounded. Where's that current flow coming from? There's a voltage right there that through physics is being changed to current flow because of a grounding path that's been established to the grid. That's in a substation. That's a 4-aught ground on the side of a transformer, power transformer in a substation. Here's another one. Look at this one, 16.2. Now that's on a piece of copper coming on a down lead on a piece of steel in a substation. Where's that coming from in this induced voltages? The chances of induced voltages or capacitive coupling between you and something energized and something de-energized is always possible whenever you're around parallel circuits, transmission lines. We'll see how they dealt with that. Paragraph Q of 1910-269, Q24 with note 1 and 2, that changed from 94 to 14 because the standard required grounding in a certain manner in 94, and they changed the whole cotton picking thing in 14 because the 94 version wasn't working. Okay, and we'll talk a little bit more about that in a minute. Whoops, sorry, I got ahead of myself. There is a graphic right there that just basically shows what Dr. Kershaw was saying. If I have 10,000 amps of fault current and I've got a high impedance path and a low impedance path, where's most of the fault current going to go? It's going to go to the lowest impedance resistant path. The high impedance path will take some. There will be current flow on everything. So therein lies the problem. You know, it doesn't matter. You know, you want to have a parallel path around your work area, but your work area will still see some fault current. So therefore, then comes the bonding. So then all of a sudden, if I bond my work area, whether it's a conductor to a pole or whatever it is, well, guess what? What do you become? You become the bird on the wire, you know. So you can actually work there, and if you can't have that one potential exposed in that work area, current can flow through that work area as long as you don't touch something else, and you can't touch anything else, then basically you're going to be safe. I found this actually out in Amarillo, Texas. I don't know if anybody from XL Energy is on here or not, but that was in your training room in Amarillo when we did a little cover-up training out there, and I said, I'm going to use that. Now, that's Ohm's law complete, okay? The top quarter of that thing is amperes, and you look at the amperes, and you kind of, you can get, if you know two of the values on anything, you can get the third value. All you got to do is do the formula. And that top one right there, and that's E divided by R. That's the voltage divided by the resistance will give you the current flow on that. So if I'm a 1,000 ohm resistor, and that's all I am, the human body's a 1,000 ohm resistor. If I'm a 1,000 ohm resistor and I'm standing on a pole touching a conductor, then I have to consider the resistance in the pole to the ground, the impedance and the connection to the ground. And if something were to come hot, I would divide all of that resistance of the pole and myself into the voltage that came in. I can tell you how much amperage is going to be there. The thing about, you know, us humans doing electrical work, the voltage is not what kills you. Current flow is what kills you. And you're going to see a video, and I hope we have time to do it all. We're going to see a video before this is over with that kind of demonstrates that. Okay. You know, your natural resistance in your hand is, you know, enough to keep 50 volts AC out, theoretically. In a perfect world, not wet, not contaminated, not damaged skin, the skin itself is good to withstand 50 volts AC. Now then, if the voltage penetrates the body and then establishes a current path to an exit, now then you've got current flow. Well, current flow through the body, it's like I said, it doesn't take much. We'll see a chart in just a few minutes. As little as 30 to 50 milliamps can put your heart in atrial fibrillation and kill you. Now, it's not going to burn you up. It's not going to do any of that stuff that higher voltage, medium voltage will do, but you're still dead. So you're protecting yourself with on the theory of parallel resistances, and keeping to the higher of the two resistances. and in bonding will keep you from seeing that current flow through your body, okay? So we'll go from there. Now then, in each one of these examples, and we're going to start going through some examples right here, and we'll talk about, yes, thank you. And we'll talk a little bit about electric utility systems. Grounded can be differences of potential. Even when it's grounded, there can be differences of potential. You saw that a while ago. You know, how does it happen? Well, it can be accidentally energized. It can have electrostatic. It can have electromagnetic, inductive, or capacitive coupling. It can be some source system. You have system voltages and source voltages. It can come from just about anywhere. It can be a mistake hooking up a generator on storms, and we're about to come into the spring season when we have tornadoes, and then it's followed by hurricanes. Grounding becomes so important then to the utility worker and to the public for that matter, but the utility worker is what it's all about. Of course, lightning can occur anytime. OSHA's definition, okay? OSHA's definition of ground is nothing more than a connection, whether it's planned or unplanned, between two sources. One being basically the earth, okay? So that's grounded, all right? And that connection right there, it may, like I said, it may be planned or unplanned, okay? And unplanned is when we get into it. The physics definition in here says grounding is nothing but the process of removing excess charge, means of transfer of electrons from one point to another, okay? So that's the comparison of the two definitions of grounding itself. Most of this is found in Appendix C. Now when you open up 1910-269 in the OSHA standards, there's 6 appendices at the end of the standard. Now they are not regulations, but they're as close to a definition of what the regulation is intended to mean. The intent of the regulation is what you need to seek to learn, okay? And all of this right here is, you know, in a ground is connection between an electrical circuit and something the size of Earth or Earth, okay? Grounding operation system includes voltages and current flow. You know, when you look at equipment and bonding, again, I'll reiterate, bonding is what saves lives. Grounding operates systems. And that's what the intent of the whole thing is. So when I'm bonded, that's a conductor. And a bonding, and I don't want to confuse the issue with anybody's policies or anything else, but let's look at it from a physics standpoint and an electrical standpoint again. A bonding conductor will never see the fault current. That's why grounds has to be rated at the available fault current at that work location. The equipment has to be, and we have a ground here, we'll get to that in a minute, and we're going to show that to you. It has to be rated, it has to be completely sized, and all that's dependent on the system operations. Is it a 2, 4, 6, 8, 10 cycle operation? Do I have 8,000 amps? Do I have 20,000 amps of fault current available at that location? So in this case right here, this is on a 345 kV line, and basically that was in Nebraska, I believe it was, when I was up there working with a construction company that was installing about 100 miles of 345 transmission line. And you see the conductor here, this basically is the bond. That is tying the pole to the downlead, okay? So when you look at what OSHA and IEEE basically requires, it has 2 requirements. You know, it causes an immediate operation of the system. That's to clear the system in a fault. And also, they have to be, this is the part here that most companies, and including the one I used to work for, we just didn't put as much time and effort into understanding. And it must be arranged to prevent an employee from being exposed to hazardous difference of electrical potential. We didn't spend a lot of time on that. But when we read N3 in a few minutes, you're going to see exactly what I'm talking about. Okay? So when it causes an immediate operation of protective devices, that's grounding. Okay? When it's arranged to prevent differences of potential to employees, that's bonding. So it's real simple. Okay? You got to have both of this. You just can't have ground you'd be surprised, and I don't know whether you would or not. I find a lot of companies that, you know, they say, well, do you do equipotential grounding? And I say, well, I do system grounding to achieve equipotential work areas. And they say, oh, you're playing games with me with words. I said, no, think about what you said. You know, basically, you can ground something, if you bracket ground something and you're working within the bracket grounds, and you're standing on a pole or in a bucket touching a pole and a conductor, and something comes hot, and that conductor is not bonded to that pole, could they be a difference of potential? And the answer to that is yes. But basically it's only going to last for 2, 4, 6 cycles. Ever how long it takes the system to clear the fault. The question you have to ask is, in your position, touching 2 different potentials in that work zone, would you be subject to hazardous differences of electric potential? And that's why they changed the Q24 in the 2014 update. Because yes, they did. And they found that out the hard way. You know, whenever you have electromagnetic induction, that is basically a capacitive coupling through the air from one conductor that's energized, okay, to another that's not energized. And you can see this magnetic field right here. If you're working in a corridor, this is a classic example. If you're working in a corridor with transmission or distribution or both, and you're working on one's hot, one's not, how much voltage is going to be on the de-energized part, okay, that's being capacitive coupled to the energized from the energized part? Well, there's 3 factors involved in that. There's 3 things you really need to talk about and consider. And that is the proximity. That's the closeness of the de-energized to the energized. Further away, the better. Okay? Closer, the more. The higher voltage of the energized, if it's a 12 kV line or a 25 kV line, that's one thing. If it's a 115, 230, or 345 or 500, that's a total different animal. And then the third factor that you need to consider is the length of exposure. That's how long is it parallel to it. Because the longer it's parallel, the higher the voltage, the closer it is, the more you're going to have induction. The more induction that you're going to have on there. I've seen as many as 6,500 volts many times on a 345 line parallel to a 345 line in the same corridor, and one's hot, one's not. And the conductor that's de-energized closest to the energized, it had 6,500 volts on it when we put a phasing tube on it. So, you know, it's not uncommon. That was about a 50-mile exposure. They were running parallel from one substation to another. We switched out one side of it to just be able to change insulators and arms out. So it's not uncommon to have, and there's some fallacies and some old sayings that went along in my world as I came along. And you know, if it don't draw an arc when you put a ground on it, it's not dangerous. That's not true. It takes about 2,000 volts to ground to cause just a small spark on induced voltages. But you could have way more than enough voltage to penetrate the skin and become hazardous to me, you know, by just, you know, getting in series between a conductor and a difference of potential. It's not uncommon. So remember those 3 factors: the distance they're exposed, the closeness of it, plus the voltage of the energized. So those 3 factors will determine how much induced voltage. This is just an example here. Everything has a magnetic field around it. You can see that here. But the size and the depth of that magnetic field is determined by those 3 factors we just talked about. You can have basically a bracket ground here, as we have, and that's your tripping ground. Some people call them tripping grounds, and some people call them other things. Main grounds, tripping grounds. I don't know. There's 2 or 3 different names I've heard as I've traveled around the United States. There's the key, right there. This is going to operate the system. You know, if this thing comes hot, and we just put a distribution circuit up here just for example, if that thing comes hot, then basically this ground is going to see it first and trip. This one here is kind of looking in the back door if it comes around the other way. But here's your work area. There I am. And basically this bond right here is bonding my work area to everything around it. So now that I've established an equipotential work zone, And without a bond, you don't have an equipotential work zone. It's real simple, okay? You've established that zone right there. Misunderstandings about equipment grounding. We'll touch on that just a little bit. And we're going to talk about step and touch potentials now. I'm going to ground my equipment so no workers underground can get electrocuted. That is not true. Popping bubbles again. To keep from coming hot. If I got the system grounded, the line can't come hot. Not true. I can push a button to turn the handle in a heartbeat. Now it won't stay hot, but 2, 4, 6, 8 cycles, or maybe up to 10 or 15. It just depends on how your relays are set up on your breakers. That's all it is. But yeah, it can come hot. Okay. And also to protect people around the truck. No. I have a lot of questions about guarding trucks versus grounding trucks. That's a whole different animal, okay? And we may or may not have time to get into all that today. To make the truck safe to touch and then to protect the public. Well, the worst thing you can do is take on if it's a bucket truck, that's one thing. About half the world don't ground bucket trucks, and that's okay. The other half does. But you got to ground everything. It's a non-dielectric insulated boom. Okay, a line truck, a boom truck, or a crane, or something of that nature. So that's supposed to be grounded. What do you ground it to? You have a driven ground over here, a screw ground. That's the rock in the pond. I've seen people drive their ground right at their feet. If that thing comes hot, all the fault current's going right, voltage is going right there. So you're standing on the worst place in the world. If you have temporary grounds, temporary driven grounds, and you're not megging them, you know, according to Ohm's law, for every ohm of resistance you build into a grounding system, there's not a lot of current flow going to go there because it's going to find another way. So consider that. But if you're pounding the ground in and you don't meg it, and you don't meg it down to about 25 ohms, which is very difficult to get to, you know, 200 ohms will work, 900 ohms will work. It just won't work as fast. But when you just put one in the ground about 12 inches and hook a truck ground to it or something, that's not a ground. That's an infinite amount of resistance. And I've seen those things come out of the ground like a rocket. When you hit them with 6,000 or 8,000 amps of fault current, watch what happens. But the biggest hazard to people is the ground gradient step currents that goes out. Like I said, that's the rock in the pond. I mean, all of the waves of energy is going to come away from that ground rod if it's working really good. That's why temporary grounds need to be about 20 feet out of the work area. And I know that's hard to do sometimes, but it's the safest thing you can do. So we'll talk more about that in a few minutes. Temporary ground, system grounds, again, are primary protection for all these things. That's induced voltage and then lightning. You know, of course, lightning can only do one thing. Now, I'm from Georgia. We have a bunch of lightning there, but the lightning capital of the United States is Florida, and in Florida, the most lightning strikes in Florida is in Lakeland, Florida. I witnessed that firsthand a long time ago when I was down there doing an audit. If you look it up, they have more lightning strikes in Florida than they do in any other state. In Lakeland area around Orlando gets more than anybody else. And I'm not sure why, scientifically why, but it is a fact. Backfeed from generators, improperly hooked up generators, it happens all the time. You can get all kinds of, like I said, there's two voltages on the system. System voltage it's supposed to be there. It's on them primaries right there that I'm sitting here looking at. And they are coming off a generator head somewhere. What comes backwards into the system would be an improperly hooked up generator, a bank of capacitors that was not cleared when you got an outage, okay, because it'll feed back into the system. If you had an underground loop that was not switched out, it'll backfeed into the system. That's source voltage. That stuff is there that ain't supposed to be there. Just the way the world is. You got to protect yourself from that voltage, okay? And these are system grounds here. This is that same 345 line here we saw where the bond was a while ago. Back in '94, and you'll see this again hopefully in a little bit, the standard required grounding not to be more than 2 miles apart. Well, when you go back and read Q2.4 right now in the notes to there's two footnotes to it. It says now that grounds shall be placed and arranged in such a manner and placed in such locations and arranged in such a manner. It's N3 that's been cut and pasted and put in Q. I discovered that one time when the standard first came out back in 14-15, and I was putting on a grounding program, and I looked and I said, wait a minute, that don't say the same things it used to. And there was a lot of oversight given to us as we were putting these things together, and they were talking about major differences in the two standards, and we hit on 4 major points of the updated 269, but nobody really mentioned grounding too much. Now, N3 didn't change, but the Q2 did. It said, the footnote now says, if I can push 1 milliamp through a 500 ohm resistor, I need to do something. That's perception. 1 milliamp is perception. 6 milliamps is like a GFCI on a 125 volt, low voltage circuit. That'll hurt you, but it ain't gonna kill you and ain't gonna lock you up. You're not gonna have involuntary muscle contraction or anything like that. But it's enough to really hurt. So now then, I ask people all the time, if I'm pulling a mile or 2 miles of wire, where is it that I have 1 milliamp or 6 milliamps of difference potential if I have a chance of induced voltages? And if you're pulling distribution lines inside energized distribution, or if you're pulling in a transmission corridor, I guarantee you, the only place, and there's a really smart fellow named George Gala, taught me a lesson a long time ago. He said, Danny, the only place a line is, when it's grounded, is the voltage. If you check voltage from that conductor to another ground at that location, is at the grounding location, okay? At the grounding location. The further you get away from that ground, and this is why they changed the standard, if it has a chance of a capacitive coupling induced voltage, there will be a difference of potential. Well, at the point where you get 1 milliamp that I can touch it and something else and get 1 milliamp, then I got to start adding grounds. It don't tell you where to put them, how many to put. It just says if I push a milliamp through a 500, that's half my body. Through a milliamp of current flow through a half of my body, then I need to start paying attention and fixing it. So, and that is the standard. That's what the regulation says now. That's 269 Q24 footnote 1 and 2. So think about that. Also, I didn't mention it. I don't know if you actually flag grounds or not. This company right here chose to do this back in, early 2000s, because when you had multiple ground sets up, especially on trouble, like on storms, it's kind of easy to drive by them and not see them. And so they started flagging grounds, and they never had another issue. It's not a regulation. It's just a good work. It's just a good, safe industry work practice. You got to remember something. OSHA regulations are the minimum safe work practices. The minimum. So that's really important. I like to do more than the minimum. Okay. Here's the chart I was talking about earlier. 1 milliamp, I just barely can't feel it. That's perception. Okay. When you get to about 5 to 10 milliamps, 5 milliamps, the GFCI on 125 volt low voltage circuit set 4 to 6 milliamps. It's got a trip. So 5 milliamps is going like, holy crap, what was that? It's going to get your attention. But at 8 to 10 milliamps, you have involuntary muscle contraction. If you're touching something with your fingers like this, it'll wrap your fingers around it and you can't let go of it. And that's involuntary muscle contraction. So, that's clinging current. Some people refer to it as clinging current. You're getting pretty close to dying right there, by the way, because when you get to 25 to 30 milliamps, and according to the tests of EPRI years ago back in the 70s, that actually stopped a heart muscle and caused atrial fibrillation. And they did that on a pig of all things, but it was the way we did it back then, and it showed then that pig's heart's pretty close to ours, and it reacted the same to electric current flow. When you get over 50, that's an assured heart stoppage situation. Atrial fibrillation sits in, your heart goes into fibrillation. It doesn't have sinus rhythm anymore. It's just sitting there doing this, and it's not pumping. And now you've got just a little while to do an AED or CPR, and maybe get the heart beating back good. So the misconception I think in a lot of people that I found is that you don't have to get burned up to get killed. You can be just as dead. How you like that? You like that, Noah's got? I know you heard it. Let's do it again. There's a dumpster over there being disposed of right now. You never know what's going to happen during a movie. But you see when it gets on up higher and higher and higher. Now let's put it in perspective. Look right here. A 100-watt light bulb is only 800 milliamps. We're not even up to an amp yet. We're not even up to an amp. So I always say your body's a pretty good conductor of electricity. We just can't carry a lot of load, because when we start putting a load on it, that's when our heart stops and we're in trouble. So this is just a little simple graphic right here. If I have a very low impedance and resistance path, that's Z, then I'm going to have a high current flow. If I have a high impedance, I got a low current flow, and it parallels that. If the impedance is low, the voltage will stay higher and the current will stay higher. And just opposite, if it's high impedance, the voltage will drop off quicker. Ohm's law says basically if I pass a voltage through a resistor, the voltage starts collapsing based on the timeline. And we're talking cycles here, not seconds. Okay, that's the main thing. So let's look at N. This is basically what we've been talking about. This is the regulation right here. This section applies to grounding, generation, transmission, and distribution lines. Okay? Technical grounding equipment is required elsewhere in the section. And here's your note. N1, paragraph covers generation, transmission, distribution lines and equipment when this section required, whenever the employer chooses to ground. Holy crap, what did I just say? Do we have a choice as to ground or not? Yeah, according to the regulation you do. And you'll see it here in just a minute. For any employee to work in transmission or distribution lines or equipment as de-energized, and one word you'll never see in a regulation or policy or nothing, you shouldn't see it, is dead. One of the two worst words that you can use any time to describe a situation is that, I'll go over there and kill it, Danny, and I'm going to say it's dead. It's never dead. According to the regulation, we never consider it completely dead. It's de-energized. If it's been de-energized and has not been checked for the absence of voltage or presence of voltage and grounded, then it has to be treated as energized. Okay? And if it's energized, then the two-man rule applies, the cover applies, everything applies. But ladies and gentlemen, to be honest with me, you and I both know that when people say it's dead, it's not, and it's not been tested for voltage and grounded, it's handled differently. And most of the time it's okay. And that's basically one of the problems we have in our industry is the complacency that's developed by work practices just by the nature of the beast, is that we don't follow the regulations all the time as the regulations are written. And that's just not a good thing, okay? So, employer shall ensure that the lines and equipment has been de-energized under M of this section. Now, M is basically the paragraph before N, and that says to de-energize, check for the presence or absence of voltage, and then ground it, okay? So, to work it as de-energized. Now, ensure proper grounding of lines through N3 through 8. So we'll get to those in just a second. Now then, here's a couple of Where's Waldo pictures, okay? Let me show you what I run into. And let me get something straight right now. I am not throwing anybody under the bus or talking down to anybody about, well, they didn't do it right, blah, blah, blah. I think in most of the time, people just don't understand, okay? Now, it's kind of hard for you to see that picture right there, so I took and blew it up a little bit. If you can see that picture, look very closely at the grounds. There's the static wire, the shield wire up there. So what have they done? Is that grounded? No, that's shorted out. That's all that is a direct short. If it were to come hot, would it operate? Sure it would, because it's a dead crossface. But if there's induced voltages, and on this case right here, the other end of this, they were making up on this pole. This is a 345 line going into a substation off of a wind field, okay? And the other end of that 345 is deaded in on a hot switch with 345 bus running all around it. These guys that's in these two buckets right here was screaming and hollering, this stuff's eating me up, it's eating me up. And the person that took that picture, I did not take that picture, but they sent it to me, a friend of mine did. And he said, Danny, look at this. And I told him, I said, yep, they just made one big wire out of 6 little ones is all they did. They have not got it grounded, they've got it shorted out. I actually found that same situation in another location in another state, and I won't mention the state because it doesn't matter. But in that case, it was a 69 kV line instead of 345, and the guy bridged the gap between the conductor over the insulators to the pole, and he became clinically dead and had to be shot 3 times to get him back. And that was the second time it had happened in about 18 months. And I'm saying that either somebody don't understand grounding, that's what I keep going back to, the principles of grounding. Why does current flow the way it does? How does voltage build up on something when you have induced voltages? The opportunities, if you will. And these were journeyman linemen in these 2 Class A buckets right here. They had been through a junior apprenticeship program and graduated and had a journeyman's ticket in their pocket. And that's how they were grounded. Like I said, I'm not throwing anybody under the bus, but we need a better understanding and a better training program of how to ground to protect us while we're doing the work. That's all I'm saying. Okay? You go on, here's the exception. You know, I told you, I said when the employer chooses to ground, and that's something I never knew we had a choice, but we do. Okay? However, if the employer can demonstrate that the installation of the ground is impractical, or that the conditions resulting from the installation of a ground would present a greater hazard to the employees than working without grounds, the lines and equipment may be treated as de-energized. Okay, we done talk with that's switched out according to M, checked it out, it's voltage and grounded, and then take the grounds off, provided the employee has established all the following conditions, and that ensures that everything's been switched out according to M, no possibility of contact, and then the hazard of induced voltage is not present. So how am I going to do that? When would that be practical? What would be the greater hazard to ground than not ground? Well, you have some situations where you have circulating current. You also have a situation to where if you're working on a grounded line and there's a nearby fault on it, you have a voltage rise on everything on there that's touching the ground. Okay, so if you're touching 2 different potentials, a conductor and the pole, or a conductor inside, and I've got an example here in a minute. I always try to give you an illustration to support what I'm saying, because I don't want you to just take my word for it. I want a scientific example as to what can happen to you. And that's the kind of the way I operate. Okay. Appendix C, again, back in the 269 standard at the bottom of the standard, you could go back into Appendix C and talks about step and touch potentials. Here's the M3. Now listen closely. Equipotential zone. That word, phrase never changed from 94 to 14. It says exactly the same thing. There's one addition. That's the bolded words that you see. Temporary protective grounds shall, when you see shall, no questions asked. No ifs, ands, and buts. Shall be placed in such locations and arranged in such a manner that the employer, now then, the finger used to point back at us, the employees. Now the employer has to demonstrate or ensure that will prevent each employee from being exposed to hazard difference of electrical potential. Again, doesn't tell you where to put them, how many to put them, what size to put, doesn't tell you nothing. It says what? It says ground. Single point grounded, yes, it works fine. Bracket grounded, it works as long as you do it safely. Half the world is still bracket grounded. A lot of people are single point grounded. And I've never been a strong proponent of it, but it works. According to physics, you can't deny it. As long as you bond, and as long as you don't get those grounds too far apart where you got circulating current, and if you do both of those and don't bond, I've got a fatality in here we may or may not get to, because it's the very end of this program. So, and all it was circulating current on grounds. And that's because it was grounded way too far apart. And he did not bond a mechanical bucket. It was a crane basket, is what it was. He didn't bond that to an overhead shield wire that they were changing out. I think they were taking down a static wire and putting in OPGW or something. And he basically got in series between the steel crane basket and the conductor and killed it at 300 volts on it. So, ground shall have an impedance. Now here's the important part, and this is where we're going to get into what I love about bierermeters right now, what they're doing in supplying the industry. I just walked through their shop and looked at what they're doing when it comes to ground sets, and I love it. I mean, it is the best method of building a ground that I've seen lately. And I'll show you one in just a minute. I'll have an impedance low enough. How can we, the employee, build an impedance in a ground set? Think about that. You know, I inspected an operating headquarters one morning right after I went into field safety. I was one of those, you know, outlanders. You know, I basically like to do more than what the minimums are. I just, that's the way I am. I fly airplanes for the fun of it, and when I'm VFR, I don't fly in IFR because I'm not an IFR rated pilot. I'm VFR, visual flight rules. Okay. Can I? Yeah, I could, but would I? No. Got better sense. So I want to do more than the very minimum. Okay, when it comes into this. But anytime you bolt something together, you don't clean a conductor, you don't use the proper clamp. Every time one of those actions happen, or if you don't torque the nut down on the ferrule to the cable, it's been squeezed on the cable, every one of those mechanical connections represents a chance to add impedance resistance in a circuit. When you add impedance and resistance in a circuit, you're not going to have current flow there. It'll either burn itself out in the clear if you hit it with enough fault current, or it's going to cause a diversion, according to Dr. Kershaw. It's going somewhere else, and it may be go through you. And then that law of parallel resistance goes to crap. If I'm a 1,000 ohm resistor in a circuit, how much resistance is in a ground path? If I've got a ground hanging right next to me, you know, and usually it's somewhere between about 6 and 8 ohms. I don't know. You know, it depends on the size conductor. It depends on the fault rated clamp and how it's put together. Whether you clean the conductor when you put the clamp on it, because you got 2 connections on each end of that thing. So you have a lot of opportunities to add resistance to it. But if you do it and do it right, you're okay. Now here's the American Society of Testing Materials. Here's basically, this is what they're doing at bierermeters, and basically ASTM 855, that's the guidelines for protected ground and equipment. That tells you about the ground fault rated clamps and ferrules and all that stuff. And then the 1048 right here, you know, contains the guidelines for selecting and installing the equipment. So you got two consensus guidelines that tells us how to build them and maintain them and how to install them. So, but if, well, like I said, when I inspected the grounds, there was like 4 big bull gangs, a couple of 3-man crews, underground crews, and a couple of troublemen, servicemen in this headquarters. And it was raining one day, and I said, let's just inspect grounds, guys. When's the last time you, oh, they've done that before. Okay, let's do that. We laid them all up on the dock. I came down through there with a meter and started checking, and really wasn't checking for, you know, for ampacity. I was just checking for continuity and then doing a visual inspection. 60% of the grounds failed. 60%. I said, now look, guys, we put them on a rolling flat right here to send them either to get repaired or send them to salvage, make jumper cables out of them or something. I don't care what you do with them. But you're hanging your life on these things, and they didn't pass the test. That's a bad thing. That is not a good thing at all. You know, testing for voltage is required, and it's the old buzzing and fuzzing thing that I used to do years ago with a 12-inch wrench on the end of a shotgun stick or a pair of 9-inch pliers that's standing in the bucket on distribution. Is not acceptable anymore. It's got to be an approved voltage tester, okay, to test for the absence of, that's the old style here, and this is the newest one. I found one of the newer ones there, and that's a pretty good meter, and I got that for a crew that was installing number 2 7-strand copper for a tracer wire for fiber optics buried on a 230 right away. And it had a pretty good report on it as far as weatherproof and all that. So On the N6, it says here, the employer shall ensure when the employee attaches the ground line to equipment attaches to the ground end connection first. Well, you know, I think some things shouldn't have to be said, but every once in a while, and I stood on a right-of-way on 100 and I think it's a 138 kV double circuit, it was in North Carolina, and I was standing there watching a contractor ground those 138 kV lines, and basically they there was an apprentice in a two-man bucket, and there was a journeyman in there with him, and he started to put the clamp, the end of the ground clamp, see the temporary protective ground, on the phase first, rather than he was going to steel. He had a flat clamp on one end and a phase conductor clamp on the other. And I hollered at him, I said, "What are you doing?" He said, "I'm grounding." I said, "Really? Look what you're doing. Where's the other end of the cable?" "Oh, it's here in the bucket." I said, "Really? All right, so now then tell me, if you put that on that conductor and you touch that and touch that steel, what's going to happen to you?" Oh, well, that's what you're down there for. And I said, "Well, I'm glad I was." Try doing it the correct way now, and that way would be the safest way. But anyway, that's actually a regulation, a standard, and it, you know, for lines of equipment 600 volts, they actually changed that in 14. You can actually check for the presence and absence of voltage with an approved voltage tester and put secondary grounds, if you got vice grip grounds or whatever, and you're putting them on like an underground pad mount transformer on distribution, you can actually put anything on 600 volts and less on with your rubber gloves once you've used an approved voltage tester. So, and the same thing with removing them, okay? You put the grounded in on first, and take the phase conductor off first, and then the grounded in off last. So it's last on, first off. That's basically what it is. Cleaning the conductor, this is another really important thing a lot of people don't do. All conductor, whether it's copper or aluminum, is going to have an oxidation process. The closer you are to the coast, the worse it's going to be, okay? And you will have an oxidation on there, and that oxidation will increase the resistance of that electrical connection. Because that clamp is nothing but an electrical connection. Whether you do it by hand or whether you do it by stick and a brush, it doesn't really matter. Just clean it, okay? Just clean it. Same way with removing, just like we said, last on, first off. Basically, here's one that's been in my program for a long time, and I think this is one that was made at the company where I work. And you can see this is a 2-aught ground, okay? And you see there's a heat shrink on it. The ferrule is squeezed down with a solid die. At this point, I'm going to get this ground that I got right here. I want you to see that. Which one? Let me go to this camera here. I want you to take a good look at this right here. This is heat shrink for mechanical. This is where the twisting goes on. That's the nut that has to be torqued down to the clamp. The ferrule, you can see, I hope you can see that. That ferrule is mashed with solid die. It's a special tool. I've seen a lot of them mashed with narrow dies. I've seen some mashed with a little dimples. They'll pass a continuity test, but they will not pass a ampacity test. Because if you don't have a solid connection right there, and a fault rated clamp, and that's a special clamp right there, Breer makes these too. So this is, I call it the cat's meow right here. You know, that's a nice cable right there. It's well built and maintained, and as long as you take care of it and don't drop it off a pole or out of a bucket on concrete, it'll take care of it. It'll operate that system, and that's exactly what this ground is for. Your grounding clamps and capacity and cables at that location should be good for any point on that line, okay? Now there are some companies, some of my customers, they have unique situations where they have multiple feeds coming in on their transmission lines, and basically sometimes they have to parallel because the configuration, system configuration, when you have 269 breakers looking at one line, that's going to take longer to clear. You're going to have more available fault current, depending on the impedance of the power transformers or the step-down transformers from, you know, with 161 or 230, 345 down to 69 kV, whatever it is. So that's an engineering thing. But then when you need to know what the cables are rated, and that's why I've got this on here. Let me get the pointer, stick, what do I do with it? Here. You can see here, most companies use 2-aught for secondary and 4-aught for a substation. And if you'll look here, you see here, this is ohms per foot, okay? And a 2-aught ground, ohms per foot is 0.07793. All right? Well, we'll round that up to 0.08. If the ground is 10 feet long, which is typical distribution ground, if it's 10 feet long, so now then, if we rounded that up to 0.08, now I got 0.8. So I got 0.8 of an ohm in the conductor itself, what we just showed you, for a 10-foot ground. Now I got to put a ferrule on it, I got to put a clamp on it on both ends. Now I got to clean the conductor on both ends and then apply the clamps. So every mechanical connection probably raises the amount of impedance and resistance in that thing just a little bit. So you think about this, it's really important to clean the conductors and to make sure those things are in good shape. We were talking a little bit about here how important it is to have the lowest impedance you possibly can. Here's your parallel path around you. If you've got a ground set that's got 8 or 10 ohms at the max, they should probably less than that really. If you've got a ground set, and I'm a 1,000 ohm resistor, according to Dr. Kershaw, where's the current flow going to go? So it's going to go to the ground set. So, and that's for tripping grounds. Now also, how good is it? Okay, what is it good for? 2-aught ground for 15 cycles, 1/4 of a second. It's good for 33,000 amps. There's not a lot of circuits, unless you got some really creative engineering going on, that's going to have 33,000 amps on anything out there. Normally, on a 12 kV or a 25 kV substation circuit, 3-phase distribution circuit, you're going to wind up with 8 or 10,000 amps at the substation. Now, if you go 2 miles away, it's going to be less than that because Ohm's law is going to kill it. It's going to kill the voltage and kill, just like we showed the graph earlier in the presentation. So for 30 cycles, it's 26,000. So I can let it burn for another 1/4 second, and then it's a 1/2 second burn now, and it'll still hold 26,000 amps before it comes apart. And that's the most important thing. That's basically demonstrating the law. You can't deny it. It's just the way the world is. If I'm a 1,000 ohm resistor and I got a ground here, basically the installation and maintenance of that ground is taken care of, I'm in better shape. Holy moly, wind getting up. Front coming in. Sorry about that. We have all kinds of external noises going on here. Here's basically just a little schematic of it. And you think about this being the source here. Now I've got 2 exact paths with the exact amounts of ampacity on each path. Theoretically, according to physics, I should have the current flow should split exactly equal. Well, I don't know. I'm glad. It's getting noisy, guys. I hope y'all can hear it okay. Theoretically, you can basically say it splits exactly half. Not really. It depends on how far this point of connection is to this one. You'll lose just a tad in between those 2 parallel points. So, just bear that in mind, okay? So there's the bottom line. The parallel circuit has the characteristics and basic rules. The sum of the currents between the 2 paths should be exactly the same. Whatever left is going to come back, okay, or it's going to split and come back equal to the amount. What you don't want to do is get in series with anything. You want this parallel path around you. That's the main thing. Because there's the 1,000 ohm path and here's the 10 ohm path. Now then, again, according to physics, that 10 ohm path is going to protect you. If you bond, that's another thing. Let's look at the difference of potential across these touch points. If I took a voltmeter and had an open gap right there and checked the voltage, it's 7,200 volts, okay? If I put a small resistor across that open point and I check the voltage again, I'm still going to have about 7,200 volts. It may drop over here. The voltage may drop just a tad because now I've ran it through a resistor, but not much, okay? Now if I were to put a solid jumper across here, there will be no voltage, no difference of potential between the 2. Now if I bond here, and you know what the little resistor is? That's me. That's you while you're working there. We're about to lose our tent. I think our curtains anyway. It's getting really windy here. So, a resistance-free jumper, there'll just be no difference of potential here whatsoever. But you see, here's the key to the whole thing. This is why a bonding jumper is so important. Even though I may have 2,000 amps flow around this, I'm still going to have about 15 milliamps go through it. Now I can feel 15 milliamps and that's uncomfortable, okay? So how do I keep that from bothering me? And that's when I put a bonding jumper in there. It's kind of like the way we used to do it a long time ago. We'd bracket ground and think everything was hunky-dory. And this is just a simplified version of bracket grounding right here. And if I were standing on that pole or standing in a bucket touching that pole and that conductor, and this came hot, the question you have to ask is, would there be enough difference of potential between myself and the pole touching the conductor? Yes, it's grounding, and yes, I got tripping grounds on it, but would there be enough difference of potential right there to be harmful to me? And that's the main thing. You know, that's the old bracket grounding method. If you want an assured grounding path to where you're going to establish that equipotential zone, basically, you do this, okay? You have a pole band and you bond the pole band to the neutral and then bond the primary conductor to the pole band. Then, of course, you're going to introduce a greater step potential at the bottom of the pole. Wherever you have a down lead, now I know all companies don't put a down lead or a ground lead on every pole. They put them on equipment poles. Wherever there's a lightning arrestor, you ought to have a pole ground. But you can also be assured that wherever there's a down lead, now when you go back to Ohm's law again on a multi-grounded Y system, if I were to go one span away from that, would I have the same amount of step potential there as I do here? And the answer probably would be no, because every down lead that you have is going to dissipate the voltage even more. The advantages of a multi-grounded Y system. So, but you're still going to have some, okay? And these are just some pictures here of grounding leads on transmission structures. I pointed out for this, you see the short jumper from the static wire to the steel. I think some companies might rely on the mechanical connection of the static wire to the tower right there, but there's not an ampacity rating on that, so it's best just to put a short jumper up there. And like on a bundled multi-phase transmission, same way. I have had people say, well, Danny, we just want to ground one conductor of the three conductor bundle on each phase. Well, then you're depending on the spacer then to become the connection between the phases, and there's no ampacity rating on that. So think about it. Now this is straight out of the appendix right here. IEEE came up with this formula, and I'm sure it's accurate. I know it's accurate, but it's also probably, you know, the minimums, all right? In the 1048 IEEE guide for protective grounding right here, where current is I, okay? I being divided by, equal to, divided, the square root of time divided into 116, and that represents about 95% of the population weighing about 110 pounds or more. The equation is valid for a half a cycle, 83 ten-thousandths of a cycle, up to 3 seconds, which is 180 cycles. 180 cycles inside a connection point, you know, if it's improperly grounded and you don't have a good parallel path, that's a long time. That's an eternity. You know, that's probably death. That represents it anyway. So voltage gradient distribution curve is absolute when you have a pounded in ground or a down lead grounded to a ground rod. This is kind of a simplified graphic right here of what's going on. We energize the ground rod, and you can see here across the way, these lines of potential get further and further out, and finally they dissipate. I kind of equate it to a rock in the pond. A splash, perfectly symmetrical rings going out in all directions until they finally dissipate and flatten out. Well, that's kind of the way fault current does when we have an abnormal condition on it. So the voltage dissipates through that grounding electrode. Now there's a resistance when that ground rod is in the ground. The amount of rod in the ground will determine the amount of resistance, you know, for the electrical connection, okay? So the voltage decreases rapidly as it goes away from the rod. Just like that rock in the pond, that wave gets smaller and smaller until finally it dissipates. Well, electrical fault current in an abnormal condition does pretty much the same thing. Ohm's law says I'm running it through earth, that's a resistor, and if I run voltage through a resistor, according to Ohm's law, voltage will decrease. The more resistance, the more rapid the voltage will dissipate. And of course, that, like I say, that's voltage, that's Ohm's law at the very least. Typical voltage gradient distribution curve, assuming uniform protection, uniform soil. And that's kind of what my picture looks like. You know, the problem is we don't have a perfectly symmetrical circle from an abnormal point in the ground. What we have is a very irregular amount of lines of potential. And it's all based on soil composition, okay? So when you, and what Harrington and Martin, this thing goes all the way back to 1954, if you can see that. They did this. What they found is every 2 feet across the surface of the earth, the grounded, well, after that rod is pounded into the ground, you know, we have a dissipation of voltage. And when you put the measuring devices about 2 feet apart, you know, how far out will it go? And in their test, at 12 feet out from the ground rod, they still had about 10% of the voltage that they put on it. So, and step potentials is very, you know, predictable, I guess you could say. But it all depends on where you're at. If you're in sandy soil, it's going to dissipate a lot quicker. Sand is silica, that's, you know, an insulator. So it's going to stop the voltage quicker. If you're down there with me, I got that big old rock sticking out of the ground down there at Stone Mountain near Atlanta. And we had to, back in 1971, we had a young truck driver at the time stick a boom truck into 115 kV transmission line, hot. And of course there was 3 or 4 people around that truck. One of them had his leg irons on, his climbers on. He was standing there flat-footed on the ground just like this. And he was 42 feet away from the truck itself. And when he touched that 115 kV phase, that 70 kV, whatever it was, went to ground through that truck and it went out, it killed him. Now there was 2 other people, it was about 20 feet away, that didn't have their leg irons, their climbers on, standing there with rubber boots on, and they never felt a thing. You know, that's one of those unfortunate things, and that was a learning lesson for my company. And from that point on, we grounded trucks before the standard was even written, and we also wore super dielectric overshoes whenever there was abnormal or the possibility of abnormal conditions out there. And that is thumping a cracked cable on the underground, opening and closing a switch or a breaker. I mean, the fire may be up there, but the fault current's coming down the down lead to the ground. And you have to protect yourself from the step potentials. If not, it could be like this. Now that's a primary laying on the ground right there. That is back in Georgia at one of my co-ops. And this primary fell on Saturday afternoon, and the gentleman that owned the farm went out there and he saw this. And he called the co-op and said, look, we've got a conductor down on the ground, I can hear it, it's frying. So it did not generate enough fault current to operate the system, okay? And just because something laying on the ground don't mean it's dead or de-energized. You know, a lot of people say, well, it's dead, it's on the ground. No, it's not. Well, anyway, it took about an hour and a half for the serviceman to get out there. It was on Saturday, and he was on the other end of the world, so time he finished his call up and got over there, Mr. Ed had come walking out of the daggum barn, and that's as close as he got right there, about 6 or 8 feet from the conductor. And of course he's got 4 feet on the ground instead of 2. And as he was walking up, the fault current went up his front legs, through his body, and out his back legs. That path was much less than the distance between his feet. I think, you know, for me, now I know I'm slow, you know, and I'm old now. But I've learned a lot, and it never was explained to me. It's not the voltage on the ground or what you're protecting yourself from, it's the differences of potential between your 2 feet is what you're protecting from. The further apart your feet are, the greater resistance. The closer they are, the less resistance. So if you were in a situation to where, you know what they told me? They told me to stand on 1 foot if a truck ever come hot. Now how long can you stand on 1 foot? No. I call it doing the toe heel shuffle. Is never let your feet get separated. You you let the heel of one foot stop at the toe and then slide the other one up. And that basically, that toe heel shuffle, you get out 10 to 15 feet, and I'll show you why in a minute. You know, if you're on a distribution line, transmission's further, but a distribution line, I guarantee you, you'll probably be in pretty good shape. And this is just kind of a graphic showing what it is. And we did a test at our test lab. We have a high voltage test lab in Forest Park, Georgia, near where my office used to be. We found out the further you get away from the faulted condition or the abnormal condition or the pounded ground, the temporary ground, the better off you are. But you can still be in a position to where you get hurt. Now, there's those dielectric overshoes. A lot of people, well, in 14, they said, oh, well, dielectric overshoes now is secondary protection. That's fine. That's the standard. Changed that. Okay? It's the secondary protection. Primary protection is the equipotential ground mats that's placed down on the ground and attached to the vehicle. Well, y'all don't know me, but I'm the one that's going to ask the questions. How do I get to the mat? If I walk up to the mat, am I not doing the same thing as, before? And a lot of people say, well, you shouldn't wear super dielectric overshoes and stand on a mat. Why not? Why not? But anyway, I say this, that there's a place and a time for the super dielectric overshoes. I've been wearing them since 1974, since just after that man got killed on that right-of-way. And I have, as long as they're taken care of and inspected and replaced when they're damaged, and as long as you don't compromise the upper, with snow or ice or mud or grass up to your legs, things of that nature, wet grass, they will protect you. I've never known anybody to get hurt wearing overshoes. Here's our test. We drove a ground rod in the ground and then put 7,200 volts on it. And this is good old Georgia red clay now, okay? And what we found here is that about 6 to 8 feet out, we had 1,300 volts between the 2 feet, those two sensors. 1,300 volts. That's way more than enough to kill you, because you don't need 50 to get in you, okay? Even out at 12 to 14 feet, we still had 100 volts on the surface of the ground. I always say get 15 feet. If you're going to drive a temporary ground rod, get it 15 feet out of the work area. I like 20. Get it as far out of the work area as possible, and put if there's going to be the chance of ground graded step currents, get it out there, away from me, okay? How does the system become accidentally energized? Well, system source voltage, electromagnetic, electrostatic fault, all those things will heat up something. Here's an example here that I was telling you. This basically demonstrates the possibility of the rise of voltage in a faulted condition. Now, excuse my drawing, but this is my attempt at CAD drawing with PowerPoint. So it worked, okay? It may not be as pretty as a CAD drawing, but basically this is a single phase takeoff off of the 3-phase line with a 65 amp current fuse. This is on hard with 5 transformers on it, okay? So what happened here during Hurricane Katrina now, of all time, it's been a long time now, this first pole right here was blown down in the storm. It blew that 65 amp fuse, boom. So the troubleman went out there, started riding it. He looked down here and saw the pole laying on the ground. He said, well, that's probably it. So he stopped and he cut that jumper right there and he put a ground on it, okay? And then he rode the rest of the line out and it was good. And he went back down there and refused that line fuse, boom, closed it in. It's good, we're good to go. We're good to go. Got everything on except these 5 transformers here. So a little while later, I don't know how long, well, one of the crews I was supporting went over there. I was a little ways away when it all happened. But they went over there, and of course when they got there, they checked the jumper cut and folded back. It was grounded, boom, that's good. Had a tag on the pole, that's good, that's paragraph M right there, okay? So they came down here and opened the cutouts on all these other transformers, and then they went and pulled these 2 meters on this, the 2 services coming from this 1-aught triplex to the service pole. So they had a deadline clearance, if you want to call it that, between the open and cut jumper, transformer fuses, and 2 meters. So they're totally isolated, correct? They're good to go. So they started to work. They set the pole, picked up the primary neutral, hung the transformer switch and arrestor, got everything connected up, was actually in the process of putting this 1/0 triplex back up. He had deaded it in, and he had the neutral in his hand, was bringing it around to tie it to the low side neutral of that transformer. So you can picture that in your mind. And about the timing's everything, it always is. He had the transformer tail in this hand, which was tied to the system neutral. He had the neutral of the triplex here, which went to the two houses. About that time, somewhere over here, there was another transformer. A squirrel stepped off a CSP transformer and stepped onto a lightning arrest. Boom! There went that dadgum fuse again. This guy screamed like a pig. He thought he was dead. And he was on the neutral. I thought when it was grounded, it was dead. And didn't I hear that somewhere this morning? Yeah, I did. But you see what happens when you have a faulted condition, voltage goes in all directions according to Ohm's law. And he was close enough to it that he had a difference of potential between these two driven grounds over here and then that neutral he had in his hand. And basically, it didn't last but a second now. I mean, the thing operated the system in about 2 or 4 cycles and then blew that fuse and cleared the fault. And of course he did. It didn't hurt him. It hurt his feelings. And he had leather gloves on. He didn't understand what happened. And everybody got all excited like, well, my God, it was grounded. How did he get shocked? And basically he got shocked on the neutral. He got in series with 2 different grounds. In a faulty condition, you're going to have that. And so, you know, there was a big discussion about that. And then, of course, then I asked the question, how can I avoid that? Besides, short of wearing rubber gloves when I'm typing that service up, which nobody does, okay? Nobody, well, some people do now. But anyway, the only way we could do that would be what? Do something that you were told never to do, and that's open a neutral. You know, they'd have sent me home if I'd have opened a neutral up when I was an apprentice. They'd have said, oh my God, what are you doing? But what it did here, it isolated it from the system, and when the voltage rose over here, they would have never seen it here. So it would have been totally isolated if it was not touching any way. And the line, you know, still grounded, it's still fine, they still bond it, ground these lines together, and all this is open, so you can't have any feedback and you can't have any nearby faulted conditions. Another thing to consider too is instead of being here, what if that squirrel had done that way back down there or way back up here? Would he have been far enough away to where Ohm's law would have dropped the voltage if it was still tied to where he wouldn't have had enough voltage to see the fault? And that's questionable. We'd had to run an experiment on that, but my theory is that if it had been far enough away from him, or if this pull-off had been far enough down and it still was here, he probably wouldn't ever even seen anything. The reality is whenever we're out there working, every time we get, if I got a neutral in this hand and I'm touching something else, I have 2 potentials in my hand. Every time. I'm not advocating wearing rubber gloves all the time. No, I don't want to get to that point in my life. But I want you to understand there's a possibility if there's a fault on a system near enough to your work location, the voltage rise on the neutral, you will see it. And if you're in series with the neutral and something of a different potential, there's a possibility of getting shocked. Okay? All right. Now, like I said, the laws of physics and Ohm's law does not change. Ohm's law and Kirchhoff's law has been around since the beginning of electricity, okay? So it's there. Fault currents, you know, if somebody closes a switch and energizes something on you, that's a bad day. You know, high induced voltages, a capacitive coupling to something that's energized and yours is de-energized. That's something else. So, you know, when you look at, this is a classic example here of how something can happen. It ain't supposed to happen. Probably never will happen. I mean, I don't think, well, I've seen lines made hot on people. Matter of fact, I heard that somebody made a line hot on a tree trimmer the other day. And also the tree trimmers refused to work on something until the company they were working for actually put set of system grounds on the part that was down in an abnormal condition. But in any case, this is my example of what I call just a catastrophe waiting to happen. Never did really completely understand how this happened the way it did, except for the good part where the guys came out of it, you know, okay. This is a 115 kV line, okay. This is another one of my CAD drawings with PowerPoint, so forgive me. This goes to Goat Rock Generation Station, which is a hydro plant on the Chattahoochee River north of Columbus, Georgia, okay. There's a GOAB, three-way GOAB switch about 20 miles this way. The generating station's about 20 miles that way. This is a 3-pole angle in a swamp. It's always in a swamp, isn't it? Can't get nothing to it. Birds ate the pole up. And so they had gotten in there to set the pole, the inside face. They had gotten in there to set that pole and came back, I don't know, a week or so later to change that pole out. So they got a switch in order. The generation operator right here, he was in charge of he wrote up the switching order, got it approved, and he was actually dispatching. The crew was in the field, was executing the switching order, just like paragraph M says. So that morning, the workers went to this pole location, but they had to park out here and take some kind of, I forgot what they had to get down, Marshmaster or something to get to it because it's in the swamp. But they had one truck stopped at this GOAB switch, which is like 20 miles out. The operator was at the substation. So the morning of the incident, the operator started a switching order, and he basically switched this load. Now there was 4 other 115 circuits coming out of this station. He switched the load to the other ones, okay? Other load, closed the transfer switch and put all the load off of this one onto the other one, and then he opened the breaker, opened the motor operated switch in the substation, and checked it open, went down there, put tags on everything just like you're supposed to do. Put a whole tag on the SCADA operating system to where nobody else could make it hot. He called the crew leader called the guy on the GOAB switch, and he said, okay, you're going to de-energize the 115 back to the switch yard from this GOAB. So open that, check all 3 blades in the clear, lock the switch handle open, and then put a tag on it. So he did. Everything's good. Now then the line is de-energized. Now then I'm ready for you to check for voltage and ground. Now what they did is they put a bucket in the right-of-way, and it was about half a span or a span and a half, I can't remember exactly. It was within 1,500 feet of the working place of the pole that they were going to change out. So they did. So there was a bucket in this right-of-way and a bucket in that right-of-way wherever it was dry enough to get to the line. So they checked the voltage and they grounded all 3 to the static wire and drove a temporary ground on the right-of-way. So not only were they relying on the static wire, the shield wire, they had a temporary driven ground and actually megged it down because they had a good soil location at this place near the river. So once they did that, system operator turned the clearance over to the crew leader and said, okay, you got a deadline clearance between open tag switches and substation, GOAB, and you're checked for the absence of voltages and grounded. You can go to work. Let me know when you get through. Fair enough. Routine day up until that point. So they went to work, and the guys, went down there in the Marshmaster. They climbed the pole. They had all their equipment there. That big wire, it's like 1295 or something. I forgot what it was because he was close to the substation. So they got up there and hung the guys and pulled the guys, and then transferred the 2 conductors. When they first got up the pole, they got up there and jumped out the conductor with a temporary ground chain because they fixing to cut that main jumper out. They also got here and put a bond between that conductor and the new pole and the old pole. So now they established their equipotential area, their equipotential zone right there. So they transferred the 2 conductors. Guys cut the old pole off, got it out of the way. And this is later on after lunch. They're actually making up the jumper. They had a big old Alcoa machine up there and was about to squeeze up this. They had a compression squeeze on. And so they're up there working on this thing. They have a shift change at the generating plant. And here comes trouble. For whatever reason, and nobody ever really figured it out, The oncoming operator and the offgoing operator exchanged information. Well, I've got a hotline tag on that circuit. I've got a clearance on this circuit, blah, blah, blah. They went through the whole thing, and then the offgoing operator left. The oncoming operator, after the investigation, said he misunderstood what the offgoing operator said. So he immediately went down into the substation at the GSU down there, generator step-up unit, and he removed the tags and removed the locks and went back up in the control room, and he closed the switch with motor operated switch, and then he closed the breaker. Boom, it came right back out. Well, he said, well, darn, it must have been a locked rotor. Reset it, and let's close it again. So he hit him twice. He hit him, and at that very moment, these two guys are making the jumper up. So they're standing on a pole with their hands on a 115 conductor. And of course, the second time he came out, he called the person that had the clearance. He said, you guys are through with that clearance, aren't you? And the crew leader said, no, sir, what is going on? He said, I just made that line hot by mistake. Are y'all okay? And of course, he's standing there looking at the crew, and the crew never even knew nothing came hot. Never knew it came hot. Never did see anything, never did hear anything. And of course, you know, I'm not an engineer by any stretch of the imagination, but you know, single phase 115 is about 70,000 volts, somewhere along in there, 68. And they say from the grounds to where they were working, and another ground set there, that they probably had 10,000 volts or more go through that equipotential zone. But because they had it bonded, and the pole was bonded to the conductor, and the conductor was jumped out, they didn't have any difference of potential, and they were actually making that jumper up. They never felt anything. So grounding, equipotential grounding works. And that's why, to me, that's why they basically said, okay, we're not changing nothing in 2014, except we're going to put the onus and the responsibility and accountability on the employer to make sure the grounds are made right, installed correctly, and maintained. So that's when it says the employer must demonstrate and ensure. Again, this is nothing more than just a little video, or a little graphic of the electromagnetic field and the capacitive coupling of the transmission distribution lines. This is what I was talking about earlier. I told you we'd see this. 1994, that's the old standard, the first 269 standard. Each bare conductor shall be grounded in increments to no point along the line of the conductor is more than 2 miles from a ground. That's when they, you know, somewhere in all that research and all those stakeholder meetings and all the IEEE engineering meetings, they said, oh, that ain't right. That's not going to work. You know, grounds are required to be in place in between the dead ends when you're reconductoring, and it'll be the last thing that's removed and the last thing in cover-up. In other words, get everything clipped in, tied in, squeezed on, get ready. When you're ready to make it hot, take the grounds off, and the last thing that comes off is the whole tag. That will end the clearance. Okay. Well, here's what it says in 14. You know, before employees are installing on existing lines and equipment, the employer shall make a determination of the approximate voltage. So now then, we've got to take a voltage reading on the possibility of induced voltages at that work location. And I use the Vermont 345, the 6,500 volts is one of them. Now then, here's what was added. This was the interesting part. Unless the employer can demonstrate that the lines and equipment installed are not subject to induced voltages, in other words, there's nothing around. There's no distribution, there's no other transmission, no crossings, no parallels, no nothing. Always put on the grounded end first, always. Attach the grounded system to the neutral or pole. Removing the grounded end of the system safety ground will be a result of contact with high levels of induced voltages. Could be a fatality. We actually had a fatality at my company back in the 90s where a gentleman, a young apprentice, was asked to take a ground off of a grounding pole band at a work location where there was 4 or 5 grounds on there coming from the static wire to the phases to the pole band, and also one going to the ground down, and then they also had an equipment ground on it. So that grounding band represented a big old junction box, okay? And when he swung around the pole to actually take that off, he took off a face clamp. And when he took that face clamp off, y'all can see the wind is really getting up here. When he took that face clamp off, that resulted in a fatality. It killed him immediately. And that was only a 115 kV line, but it was parallel to 230 lines in the same right-of-way. Again, it says the employer shall make a determination of that approximate voltage and then find out. Now, here's the picture right before the video. I want to show you this just to kind of give you an illustration of how bad it can be. This is a 500 line that was probably 75 miles between substations. This brand new 500 line was parallel to another 500 line in this corridor all the way for 75 miles. Okay. Well, the last set of grounds was about to be taken off, and they put a amp meter on the down lead coming down the structure to the driven ground, and you can see there's 65.9 amps, and there was a down lead on the other legs of that four-legged structure. I'm not sure if that Kirchhoff's law was exactly the same, but I think it split probably appropriately. And if you do the math, all four legs, and that's going to put it way up there. But I had someone do some extrapolation on there and say there's probably 100,000 volts of induced voltage on that new line. So that was big. All right, now here comes the video. Let us know if it's not working on your end, and we'll let you watch this for the time being, okay? Turn the volume up on the TV.
We're here at the Klondike Training Center to perform some testing showing induced voltages and induced currents at a work site. We have two lines that are parallel for 26 miles here. We're going to show the actual voltages and currents that are here if we were working at this location.
It's about 2
Let's get
hours.
started.
Might want to stop here after this.
Stay beside the TV because this is...
All right, our testing is going to show actual conditions on actual line. There's nothing made up. There's nothing calculated on computers. No fuzzy math. This is real stuff. This line from Klondike to where? Laurel is in parallel with this line from Klondike to Grady, 20-something miles. And Bill, you're about to ground this line. Okay, you're about to ground this closest phase here. We're following our rules exactly. Now, we just happen to have a meter on this line. Right now, we're showing 3,900 volts on this de-energized line. We call it de-energized. It's actually energized to some point because of its location next to this 230 line. We've got 3,900 volts on this line, Bill. According to our rules, do it the right way, install this ground on this line and watch what happens. We've got the ground installed. All right, we just installed the ground. Immediately, that 3,900 volts, that voltage that was on that floating line disappeared. Now, something else changed though. The current in our temporary protected ground went from 0, obviously, to 370 milliamps. Now it takes 60 milliamps to kill a man. So if you were to get a series with that right now, the way this induced voltage, induced current, the way this physics work, if you were to get a series with that current right there would be reduced, but only slightly. You would see almost all 360 milliamps. That's dead. That's dead. That's way dead. Okay? Now, a lot of people have thought in the past that by installing that ground, we have discharged this line. Okay? But let's watch what happens. Bill, I want you to disconnect that line and let's watch what happens to that voltage.
Look at that voltage jump up.
The ground was removed, the voltage jumped right back up to 3,900 volts. Nothing was discharged. And this voltage is 60 hertz voltage. It is, if we were to put an oscilloscope on that thing, it would show a pretty sine wave, just like any other energized line that we might see. Nothing is de-energized. The voltage jumped right back on. All right, let's put the ground on again and watch watch this so nobody misunderstands.
See a little spark when it comes off of
Is
it.
installed. Voltage immediately drops out. The current in the temporary ground immediately comes up. Still 360 milliamps. All right, disconnect it one more time.
Little spark.
Disconnected. We see an arc. The voltage immediately jumps up. There's no discharging. This is not a static thing. Okay? This induced voltage, induced current, it is here every time we install a set of grounds when we're dealing with parallel lines. And the parallel lines, the lines do not have to be parallel where you're located. You may be on the only transmission line in the right-of-way, but these lines are parallel 10 miles down the road somewhere. If they're parallel for a certain number of miles, this danger of induced voltage, induced current will still be here. So if you follow our existing rules, of PPE, the order that you install the grounds and the order that you remove the grounds, you will be safe. You don't have to wonder, is this a dangerous location or not? Also, it's not just the guy who's making connections up at the floating conductor. For example, if we're on a structure out there, if we're on a transmission structure, we've got our grounds all on a cluster bar. That's where the real danger is, because we have documented fatalities all over the country of people mistaking one ground head for another and removing the wrong one at the wrong time, or one accidentally knocking one off, or one falling off and reaching out to grab it real quick. If you put yourself in series in any way, that's where this 360 milliamp can get you.
So Keith, what you're saying here, behind this, is that there's a difference between static and induced voltage. Is that correct?
Yes, the static voltage was a term used for many, many years to describe capacitive coupled voltage. That's what we're showing right here. The problem with that word is it's the same word that's used when we talk about scuffing our feet on the carpet and touching a doorknob or shocking your little brother or whatever it is. That is truly static voltage. Once you discharge the voltage that you've built up, it's gone. And in order to get it back, you have to scuff your feet again and develop that voltage. Here, the source of voltage for this de-energized line is the energized line. And as long as it is energized, that voltage will be on here. We've left this ground on this line for several minutes, and the second we take it off, that voltage jumps back up to 3,900 volts because of how long those lines are parallel, how far they are apart, the voltage of the energized line. All these different factors come up to make that 3,900 volts. But it's nothing that can be bled off. The only way it'll turn off is if I go over here and de-energize that line. If I de-energize that line, that voltage will collapse.
Now ground takes ground log or substation line. These are the same risk you're talking about.
Yeah. It's very dangerous. We're all looking up at this line. We're all looking up at this floating line. But when that ground is connected, if someone were to come over here and disconnect this connection to the ground and put himself in series, he's at the same risk as that guy that would do it up top. So that's why we have our rules, and OSHA has rules that say you always disconnect the ground end, the grounded end of your ground set last.
So we used to think that the lack of an arc indicated that there was a problem. So I guess that's the understanding.
That's right. The amount of voltage right here is very impressive. 3,900 volts on something that we call de-energized is kind of impressive. And as we disconnect the ground, you can see a little arc. Well, that arc is impressive, but that's not what causes fatalities. What causes fatalities is the current, and that current flowing in the ground set. And it is very possible to have current induced on a ground set by a relative, by 115 kV line. If the parallel lines are long enough, You can have well enough, easy enough current to kill somebody, but not enough voltage to show an arc. Okay? The presence of an arc or the lack of an arc is not enough to determine is this a dangerous location or not.
Same situation, I know we're doing on the transmission line, bus clearance inside the substation. They're working on buses and stuff inside the substation. Same situation.
Well, the physics are the same. The physics are the same with one exception. If you're working in a sub in between grounds, which a lot of our procedures tell us you have to, you will not be, well, you won't be exposed to it. There has been a recorded fatality though. Somebody was cleaning, in a substation, was cleaning insulators. Okay? This whole substation was de-energized. This was not our company. But they went and they were cleaning the insulators on the switch on the outside of a breaker. Okay? The switch was open because the substation was de-energized, and they got on the switch, the line side of the switch, and came in contact with that floating conductor, and they were killed. You know, basically, it was an ungrounded line they came in contact with.
So for those of us that's doing the work, we need to remember that even though the line is grounded, there's still current.
Even though the line is grounded, and we call it de-energized, there are voltages present, and there are currents present. And as we make connections and disconnect things, we're totally changing the physics around. Okay? So what we do is we establish our grounding rules to make sure that the lineman who is working on that job will always be protected.
That's probably one of the best videos that I've ever seen, you know, that illustrates capacitive coupling and induced voltages. It just, without saying, it states the real case. There's one exception to what Keith is a, you know, was a friend of mine for years. I mean, when I worked at Southern Company, I guess he still works there. But he had Dave Wallace's ear in 2014 when he was actually rewriting the standard and basically was representing Southern Company on the stakeholder committees that actually had some input into system grounding and equipotential grounding. So, but anyway, I've got a couple here I want to talk to you about a substation right quick, and you know, we're probably running out of time, I guess, but you know, Keith just made a statement that I want to make sure everybody understands. He said, when you're working between bracket grounds on a bus and a substation, you won't be faced with that situation. Well, there are opportunities in a substation, and I was faced with one of my customers. This was before this came out. This came out here as a result of another incident in another location, but it resulted in a fatality, and it's circulating current on grounds. You know, when I first started, you know, I was the old adage, it ain't dead till it's grounded. And what I'm saying, you can have enough circulating current on grounds to kill you, and it'll kill you just as fast as, like this gentleman here found out, unfortunately, as it would be on an energized conductor. And what he did is he was in a JLG, a metal basket, a work platform, if you will, and he had it set up, and you see his ground was over here to a down lead. Now this is just a simplified drawing. This bus clearance right here was a ring bus, and I think it was a 500 kV station, and the ring bus was grounded with ground switches, which basically was, gosh, this substation was like 100 acres, it was huge. And the time the ring bus looped in and out to all the bays and everything, it was a quarter mile away. It was 1,500 feet away each direction. Well, the bottom line is his bucket was grounded here, and the bus was grounded in two locations over there, but the induced voltages was all around, and you had all kind of circulating current in the grounds because of the distance of the grounds from the work location. Well, when he got up in position to work, you know, he had the potential of that bus, and he was another potential, and when he completed that circuit right there, it became a fatality. And when they did the case study on it, when they did the investigation on it, there was 1,100 volts difference, between the basket and the bus. But now how could he have prevented that? And I guess they just didn't have the training. I don't know the details of the accident, but I do know what happened to one of my customers. Same exact thing, but just a less distance. But it was shocking him. And he was welding on some connectors on a 3-inch aluminum tube on a 500 kV bus down in Florida. And he told me, he says, I got it grounded, the bus is switched out and grounded, and I'm still getting shocked. And I said, bond your basket to your bus. Just bond your basket to your bus. And that bonding cable ain't got to be a ground chain. It can be something as small as, number 6 or something. It's not a ground, it's a bond. And all you want is an electrical connection between the basket and the bus that will balance and equalize the potential between the two. And that way there's no differences between potentials with the person standing in the bucket. As soon as he put that on there, it went away. He never had another problem. I talked to him the other day, and this has been 3 or 4 years ago now, before this fatality ever occurred. And I'm not sure where this one was at, but it did what it did. But I'll show you here, it doesn't take much. This is another incident here that came out of Mr. Jim Bones' library, and basically they were cutting in on U-Bay in a 345 substation, okay? And you can see the graphic right here. This side is grounded, okay? Switch was closed. They're putting this jumper in, it's a 2-conductor bundle, and they're putting jumpers to this side of the switch to go to the bay. Well, somebody opened the stupid switch. Guess what happened? Here. Now then he isolated the grounds. The grounds are over here. This right here is just hanging. Look what it was doing. Just the jumper conductor hanging against the steel, laying against the steel, was arcing. And when he touched it, he burned it. So it doesn't take much when you've got a magnetic field, of a 345 or a 500 substation to get enough difference of potential, enough voltage, induced voltage or capacitive coupling to arc and burn. So, as I said earlier, it takes about 2,000 volts to actually see an arc. And of course, in that case right there, it was enough for you to see. So I don't know what was on there. This was another one that came into IP that was talking about establishing an equipotential zone. And, my idea of an equipotential zone, you got to stay within it. If you get outside of it, you get outside of your zone and you're working out here, you're not in a bracketed zone anymore. So just be careful of that. This is a transformer here. This came into IP, and Jim and I talked about this quite a bit. When they lifted the jumpers off of this power transformer, somehow, I don't know whether they were doubling the transformer or whatever they're doing, they got in series somehow in between the two, and they got shocked. So, say, what's the best method to do this? And so what we did is we came up and gave them a suggestion, is to do this. Instead of going here, okay, and around and then over there, when you lift the jumpers up, now you got to open. Anytime you open something up inside a zone, you need to jump it out. So what we said is pull your jumpers, lift your risers, and then jump out from bus to bus. That way you cannot have a difference of potential anywhere. The tank and the transformer is the same, and then the bus is jumped out across the top, and now there's no difference of potential between the bushings. And that basically solved that situation right there. Just a quick little graphic of how EPZ zones work, and these are mats. When you tie that fiber mat that's woven to a down lead, now then, if you're standing on it, now you become the bird on the wire again, as long as you don't take 1 foot off and 1 foot on, okay? Because unless you got super dielectric shoes on, it's gonna get you. You're gonna get ginned up for sure. Just don't get it serious with two different potential, whether it's conductors, whether it's a conductor and a ground, or whether it's two grounds. It does not matter, because any one of those potentials can be deadly to us, and it's just the way the world is. It's just, you want to be the bird on the wire. That's what you want to be. The bird cannot light on the wire as long as that magnetic field is not above about a 46 kV line. 69, they might or might not light on it, but they ain't gonna light on 115, 230. You see a bird sitting on a 345 line, that line's de-energized. I can assure you it is. So this is just some distribution grounding here. Grounding protection when connecting the grounds, just remember this, ground in first, okay, and then connect the formerly hot conductors or equipment with a stick. It's a stick operation. The only time we use rubber gloves to apply grounds is on 600 volts or less. Just be sure you remember that. Single point, best location, to ground as close as possible to the work area. Don't get your single point grounding too far away. And when you have bracket grounds, ground on either side of your work location. And remember this, if you open up, this is what he did a while ago in that transformer. If you open up, just remember to jump that open out. Jump that bus out inside that bracketed zone, because if you don't, you're going to have two different potentials right there. Last thing I'm going to leave you with is substation grounding here is in switching in substations. I've had to investigate 1, 2, 3, 4, at least 5 different situations where switching orders were incorrect or improperly written or was not executed properly. And in one case, they were not reviewed. They actually left a step out. Switching orders are really important. A lot of people say, well, that's just another thing we have to do. Yeah, it is. But it's very, very important to the people that's doing the work. So you want to make sure. 2 common mistakes that I have seen in my history is forgetting about station service transformers, especially if you got a 2-power transformer situation to where you got multiple circuits of station service that somehow get together in a control center or control house and can feed through and come back on the other transformer on the de-energized bus and heat the bus back up. Or you have cap banks that the cap bank is left online and not opened up with a switch to isolate the capacitor bank from the bus itself, and you de-energize the bus thinking you got it all dead. Well, it's not going to be exactly de-energized to where you can actually check the voltage and ground. If you get on it before it's grounded, you got a bad day, because the cap bank will feed back into the bus. So make sure the cap banks are included in your switching zone. Okay? These are just some of the customers that I work with sometimes, and just the benefits of the bracket ground. Do not have them too far apart. Do not have them too far apart. And then jump out anything inside the bracket that's open and just bond everything else in the work zone, for source grounding. And these are just some pictures of grounds here, of application of grounds. This is the last picture I'm going to leave you with, because this one's really important. Matter of fact, I had somebody call me the other day. They said they wanted this slide off this power plant. I said, well, sure, you can have it. Doesn't matter to me. A 3-phase distribution line or even a transmission line, if all 3 conductors are down or bundle conductors are down along with the neutral and the static wire, and we bracket ground, we're going to bracket ground here, and we're going to go over there and bracket ground on the other side. I've got 8 conductors right here, 8 ends. What am I going to put together first? Which conductor am I going to do? The neutral? Am I going to do B-phase? What am I going to do? It don't matter, because whatever conductor you put together first is going to represent the chance of circulating current on grounds or either neutral return currents. And we didn't talk a lot about neutral return currents, but if you've got a distribution substation and it's a Y circuit, the neutral return currents at the transformer, back at the power transformer going to the grid, it can be extensive, especially if you got a lot of inductive load out there, to where, like motor load, it's not lighting load. Lighting load, you won't have a lot of return neutral currents. You use it all up. But on inductive loads, on motor loads, you got more coming back than you do on lighting loads. So you have to deal with those too. So whatever you do with this situation right here, jump that first one out. Take a system safety ground and jump it out. Now then you've reestablished, because all of them are at the same potential because you got them bracket grounded. Jump that one out and put it together. But if you take a stick and put a system safety ground between one of them, now they're all at the same potential again. So you remove that opportunity, if you will, to get in series with that return neutral currents. And here's just one more thing that's really important. Knowing what your resistance is on the earthing ground, and you see there's a megger right there, electronic megger. I know it's probably difficult to see right here, but it's 90.9 ohms. That's not unusual. You know, what does National Electrical Safety Code say? If you got a multi-grounded single point ground situation, section 4, and I can't remember what it's in the last section, but it has to do with grounding. It says 25 ohms is the perfect world. Well, I can tell you how many times I found 25 ohms driving ground rods to achieve a better grounded, like a riser pole for underground when you got switching equipment on it and all that. One time in my life, I've seen 25 ohms. I've seen 25 to 50 a bunch. I've seen 50 to 100 more, and 100 to 200 a tremendous amount more. But this is hard to do, especially if you're in rocky territory. If you got rock and you know, there's a process in which you can spread grounds out and tie them all together in series and do a lot of things to try to achieve that 25 ohm. Just remember this: the lower the resistance at the grounding point, the better the system's going to operate, the better the grounds are going to operate. And that's just the way the world is. Okay? I will leave you with this. This is Puerto Rico a few years ago when I went down there, and a crew found this, and it's hard to see, but a crew found, that's a T-handle screw rod right there. It's about a 6 or 7 foot rod. It's about screwed in the ground about a foot. About that far. And he's got 2 4-aught grounds tied to it. And the 4-aught grounds are coming off of a two conductor bundle. There's 5 structures down in a row right there across the mountain down there in Puerto Rico. And they were there to clean the right of way up and get ready to start putting the structures and the conductor back up. And they had to build a road. I told them, I said, the road, you pack the dirt down on top of the conductors is probably a better ground than this right here, because that right there is not a ground. You can forget it. If you think that right there is going to handle fault current coming off of 230, I got a bridge I'm going to sell you somewhere in Arizona. It's not going to work, okay? It just ain't going to work. So just remember that as you go through it. There it is, 2017 Section 9, 96D, okay, 25 ohms. And I think that's based on an old Johnston arrestor that was all the way back into the 60s when they were making glass arrestors for polymers. And they said that a 25 ohm resistant ground was the best available ground for that lightning arrestor to perform best. Scientific fact, leave you with this thought. Every ohm of resistance you build into a protective grounding system raises the possibility of increased current, across the body in an instant. I'd rather it go somewhere else on the parallel ground than through me. And that's all I'm going to say. So establish that equal potential ground. Guys, ladies, I hope that you got something out of this today. We tried our best, and I think we probably need to fold the tent here before it blows us away, because I got a feeling that front's coming closer and closer. So thank you so much for attending this session. If you like this session and you want to see much more, let Brent know, because that's what we're planning on doing, is trying to provide the information you guys need out there to make it safer to work for linemen in the field. There's no, we've been averaging 24 to 28 linemen a year, and even 30 to 40 in some years of personnel getting killed in the field doing line work. Forbes magazine says it's the 7th most dangerous job in the world. It's not, as long as we follow the rules. We've got to understand what the rules say, the why behind the what. So please, know the rules, follow the regulations, don't do anything outside of them. Let us know how you like this, if you want more, or what topics you want. Let us know, and I guarantee you we'll provide what you need. Thank you so much for attending, and if I can ever help you, give me a call. Thanks very much.